Hi guys, this is Mrs. Ross. Hope everybody is doing well. Today, this video, I wanted to go over the rest of 3.4. I know we started this in class on Monday and kind of rushed through some of the examples, so I wanted to take a step back, talk about what we were doing, and go through a few more things that we didn't get to just to make sure everyone was on the same page. So I was all excited on Monday because we got to the point where we're actually solving exponential and logarithmic functions. And just wanted to make sure that we took a little bit of a step back and talked about the three strategies that you can solve an exponential or a logarithmic function. So you can see the three ways here in this box. One is to rewrite the original equation in a form that allows the use of the one-to-one properties of exponential or logarithmic functions. All right, so, and up here we happen to have our one-to-one properties. So this basically just says if I can get a to the x power equals a to the y power, so basically I can get the base of each of my exponents equal to each other, then I know that my exponents are equal to each other. The same if I can get a logarithm base a of x equal to a logarithm base a of y, then I know that the values x and y that I'm taking the logarithm of, those would also be equal to each other. So this is one possible strategy that we can use. Then the other two strategies, which I think we did several in this category, we'll do one more just to make sure that we know it. The other two strategies are if you have an exponential equation, you rewrite the exponential equation in logarithmic form, and then you get to apply the inverse properties. So basically, if you have an exponential equation and then you take the logarithm of both sides, then that's going to allow you to get your exponent down. And then the reverse of that's true too. If you have a logarithmic equation and you want to solve, then you can take the exponential form of both sides, and that will help you to be able to solve. So just wanted to pull that all together because I know I kind of rushed in there. I was a little excited. But just those are the kind of the three main strategies to be able to solve these logarithmic and exponential functions. All right, so let me just do one quick problem to review this idea of using the one-to-one properties, and then we'll kind of tackle some more. We were in class, we did a lot of work with rewriting the one-to-one property, and we have some more examples to go on these two. So let me, yeah, I can get it all in here. Let's pull this over. And actually, we'll do maybe two or three because there was one or two that I didn't do. So this is the strategy to solve equations where we rewrite the original equation in a form that allows the use of one-to-one properties. Okay, so what we're going to do is, I don't think we did this in class, we are going to do number 24 down here. Okay, and I'll write it bigger up here so we can all see it. So 24 is that we have 3/4 to the, I can't even see, 3/4 to the x power. Okay, there we go. Equals 27 d4. All right, so the strategy that we're going to use for this is this first strategy. Rewrite the original equation in a form that allows the use of the one-to-one properties. So if I can rewrite this 27 over 64 as 3/4 to some power, then I know that the two powers equal each other. So that's what I mean by one-to-one property. So I just happen to recognize that 27 is 3 cubed, and 64 happens to be 4 cubed. So I could rewrite my right side of the equation as 3/4 cubed. And then over on this side, we have 3/4 to the x power. And then because of my one-to-one property, I can say x equals 3. So we were doing strategy number 1, although we didn't quite say that we were doing strategy number 1. So I just wanted to follow up with that. The other thing I wanted to mention, there's just a few problems like this, but it is good to know when you're doing any logarithmic function, this applies to any logarithmic function, is number 12. Yep, number 12 right down here. Okay, so we have two equations. We have or two functions. We have f of x equals 2 to the negative x plus 1 power minus 3, and we have g of x equals 13. And one possible strategy that we haven't kind of thrown into the mix yet for solving these equations is to actually use a graphing utility to find out where the two equations intersect. So this is always a strategy for when we have two sets of equations and we want to find where both are true, right? We can always put that in a graphing utility and see where the two intersect, and that's going to be the point at which both equations are true. So that's the case actually for any of these, but it's kind of called out specifically in 12 and 14. So I just wanted to do number 12 so you know that's a possibility, and then you can actually use this to kind of verify your answers for any of the upcoming problems. All right, so what do I mean by that? Well, let's pull up our graphing utility. And we have two equations. We have f of x equals 2 to the negative x plus 1. Nope, this plus 1's got to go up in here. Negative x plus, I got to put it in parentheses. Negative x plus 1. There we go. Plus, so make sure, minus 3. So the first thing if you're doing graphing is to make sure you type it in right? 2 to the negative x plus 1 minus 3, and then my g of x equals 13. Okay, that's off my window, so I need just to pull my window out here, right? And I see my point of intersection is here. So when it looks like when x equals negative 3, f of x and g of x both equal 13. So the x value that makes basically this equation equal to 13 is negative 3. So don't forget this is a strategy. Really fast, if I would have thrown in, I know I'm skipping around a little bit, but that last fraction that we just did, or the last equation we just did, we had 3/4, right? 3/4 to the x power. And we wanted to know when that equaled 27 over 64. I'll have to do y equals 27 over 64. So the last equation that we just did, we solved, and we had found out that our exponent x was 3. So you could see that this graph would have worked as well to verify your results. All right, sorry for skipping back and forth since we had Desmos up. So for this particular one, we know that x actually happens to be negative 3, just coincidental, a lot of 3s this morning. And then if we pop back over here and scroll out this way a little bit, use a graphing utility to graph both f and g in the same window, approximate the point of intersection, then solve the equation algebraically. All right, so let's clear off a little space here since we have it up, and there we go. All right, so number 12, we're going to solve algebraically. So that simply means we are trying to, this is number 12. Got all kinds of shapes going on. Number 12, we want to find out what x value makes both true. So we're trying to figure out basically, when does f of x equal f of g? All right, and so we are going to write this equation. We have 2 to the negative x plus 1 minus 3 equals 13. Okay, so now we are going to decide which strategy do I want to use to solve this. All right. Sometimes it's not clear right away, and sometimes you might just want to do your simple basic algebraic functions before you kind of get a clearer picture. Okay, which strategy do I want to use? Well, I know that I can add 3 to both sides, right? Okay, so I get 2x plus 1 power equals 16. All right, so I'm here. My 2 strategies that I have a choice between using are, I could rewrite this as 1-to-1, or I could write my exponential equation in logarithmic form. Either way would work, but for this particular one, kind of something goes off in my head and says, oh, this is 16, and this is a base of 2, and I know that I can make 16 with 2 to something power. And so I know that I can make 16 as 2 to the 4th power. And that helps me because I don't have to deal with adding a logarithm in. I just have the same base now. And so now I can just say that because I have the same base and the one-to-one properties, that my 2 exponents equal each other. So negative x plus 1 equals 4. Do a little math, and we get negative x equals 3, or x equals negative 3. So that's what when we graphed it, right, on Desmos, that's the point of intersection where x equals negative 3. All right, so that is a review / overview of the one-to-one property. I think where we left off on Monday, we were around here in sections where we were solving the logarithmic equation. So let's kind of pick back up there after I clear off more space. That's not going to help me clear more space. Here we go. Maybe. That's what I'm trying to do. Okay, so we were just trying to clear. There we go. Great. All right, so we're in this section where we are solving logarithmic equations, right? So let's do number 38. I think we did 30 and 32 in class. So let's look at number 38. Okay, so 38 has the natural log of 3x plus 5 equals 8. Okay, and we want to solve for x. That's what we're trying to do, right? We have our 3 strategies here. To rewrite this in one-to-one property is going to be kind of difficult in the format it's at. So we are going to be using this strategy where we rewrite our logarithmic equation in exponential form. Okay, so what do I mean by that? Well, that means that if I, right now this is in logarithmic form. If I write this in exponential form, I can actually say that I'm going to take each of these sides and put it in exponent. Now, what exponent am I going to use? Well, because I have the natural log, that's easy because I know whenever I have the natural log, I'm dealing with e. So I want to rewrite this as e to the natural log of 3x plus 5. And then over here, I will have e to the 8th power. So just like all of your previous math, if you do one thing to one side, if we raise our left-hand side to the power, to the logarithm of the base e, to the exponent with the base e, then I also have to raise my right-hand side to base e as well. All right, so why did I do this? To make my equation more complicated? No, because I know that based off of my inverse properties, if I have my base and I have my natural log, these are inverses of each other, right? So they basically cancel each other out. So I get 3x plus 5 here on the left-hand side of the equation because e to the natural log, they're inverses of each other. So that just becomes the value of the exponent that's left over. All right, and then still here, hanging out here on my right-hand side is e to the 8th. E to the 8th might look like it's not kind of simplified, but that's actually a value. If you type in e to the 8th, we know the e is 2.7, whatever that number is, to the 8th power, that is a value. So it's, it is as simple as it gets. So now we can actually solve for x, 5 from both sides. And we get 3x equals e to the 8th minus 5, and then divide both sides by 3, and we end up with x equals e to the 8th minus 5 divided by 3. Okay? So that's that funness that we are solving for logarithmic equations. Let's do a quick example from 40 through 44. I think these are actually easier, and you'll see kind of the way that they're written, why I would say that they're easier. So, for example, we have number 42. Okay, it says simplify the expression. So we're not even solving, so we don't even have to use a strategy, right? So number 42 is, we have the e to the natural log of x squared. So again, by our inverse properties, we know that since e and the natural log of e are inverses of each other, then that just leaves our exponent by itself. All you have to do for 42. Easy peasy, right? 44, negative 8 plus e to the natural log of x cubed. Again, inverse, so we just have negative 8 plus x cubed. Nice, easy section there, right? Okay. All right, so then we get to these little 46 and 48. Solve the exponential equation algebraically, round your result to 3 decimal places, use a graphing utility to verify your answer. All right, so far in all of our fun, we've got to use one-to-one for solving logarithmic equations. We've gotten to rewrite logarithmic equations as exponential equations. Now we're going to get to number 2, where we're going to rewrite exponential equations as logarithmic equations. Okay, so this is number 46. And we have 6 to the 5x power equals 3,000. Okay, so now we have an exponential equation, and we want to solve, and x obviously is in the exponent spot, and we need to solve for x. So really, to be able to do that, we want to be able to get x out of the exponent, because we really don't know how to deal with that, right? So we are going to use strategy 2, where we're going to rewrite the exponential equation into a logarithmic form. So we're going to take the logarithm of both sides. You get to pick which logarithm that you want to do. I would highly recommend either doing the common log that's base 10 or the natural log, because those are readily, easily available calculations on your calculator. So I'm going to go ahead with the natural log, no particular reason, or no, I'm going to go ahead with the common log. So I'm going to take the logarithm of 6 to the 5x power, and then that means I also have to take the natural log, the common log of 3,000. I really should have just did natural log, because I really wanted to do that. All right, so what advantage does this have? Well, this advantage that this gives me is that I get to use the power rule to get my x out of the exponent. So I can rewrite this as 5x times the common log of 6 equals the common log of 3,000. Okay, and now, by the power of algebra, I can get x by myself simply by moving my 5 and my log base 6 to the other side. So my equation is going to be log of 3,000 divided by log of 6 times 5. Not 6 times 5, it should be log of 6 times 5. Now, once you get here, you cannot do this by hand anymore, so it's just said solve it algebraically. You'll see even my basic, scientific calculator on my computer has a log function on it. So we have log, oh, maybe if I write it right, 3,000 log, okay, divided by 6 log, and then I'm going to divide all that by 5. Okay, so if I do that, I find that x equals a very small number right now, a very long decimal, all right? So I find that x is approximately 0.894. Okay, and then what we can do is we can go and we can verify this graphically, right? So this is going to be fun to graph because our value is 3,000. But let's get this popped up here. All right, so the original equation was 6 to the 5x power, the very fast exponential equation, and y equals 3,000. So I need to do a little zooming, or maybe I'll just go here and go like 0 to 3,100. There we go. All right, so up here where the two intersect is at, voila, 0.894. Isn't that nice when that all the math works out? I always enjoy that. Okay. Yep. All right. So let's do one more since there aren't very many in this section. Let's tackle number 48 just to make sure that you've got it. If you want to, you can pause me and try it on your own and then come back and see if you got it right. Number 48. I'll do this in red. 48. We have 4 to the negative 3, my 3t power equals 0.01. No, 0.10. 1/10. All right, so now we have an exponential equation and we want to rewrite this in logarithmic form. Okay, I am going to go ahead and so I want to get t basically by itself, and t is up in exponent. So in order to be able to solve this, I am going to take the common log of both sides, and that's going to let me get my t out of my exponent. So take the common log of 4 negative 3t. Again, you could take the natural log too. You could take any log that you want. It should work. But I like the common log because it shows up on my calculator. All right. And so when I take the common log of both sides, that lets, by the power rule, my exponent gets to go to the front. So I'm negative 3t log of 4 over log of 0.1. Solve for t by dividing both sides. So I get t equals log 0.1 divided by the log of 4, and I should have this alpha times negative 3. It's really how I should have had it written before. Just forgot to write it. Okay, so then when I go to evaluate this with my calculator, I get that t approximately equals, there should be wavy lines, 0.554. All right, and then I will pop over to my graphing calculator. It's always fun when your numbers work out, right? So we have 4 to the negative 3x, 3t really, right? And then our y value is 1/10. So I need to change my viewing window slightly, right? Now I just need to go, y goes from negative 1 to positive 1. There we go. All right, let's check this out. And they intersect when we have 0.0, yeah, at 5. They intersect when x equals 0.554. And that's what we solved. Okay, almost there. One more example, and then I think you guys are ready to tackle 3, 4. Or maybe you're ready before this, but we'll do one last example here at the bottom. And even pop it up in the new screen. Let's do the last example here. Solve the logarithmic equation algebraically, round the result to 3 decimal places, verify your answer using a graphing utility. Okay, so we're back to logarithms. Couldn't stay away, right? We have 3 plus 2 times the natural log of x equals 10. Okay, and we want to solve for x. So let's do all of the other algebraic things we need to do, and then kind of deal with if we want to use raise it to an exponent or not. So what do I mean by that? Well, we're going to subtract 3 from both sides, and we get 2 natural log of x equals 7. And then I know I can divide both sides by 2, so I have that the natural log of x equals 7 over 2. Okay, so now I'm down to kind of my basic form of my log, the same equation, right? I just used algebra to simplify it down. I don't think I can use my one-to-one properties, so what I think I'm going to use is I'm going to change my logarithmic function to an exponent function. So since it's natural log, I'll say it's e to the natural log of x equals e to the 7 over 2 power. And then this, because they're inverse property tells me this is x equals e to the 7 over 2 power. And let's see if my little scientific calculator can calculate this for me. Might have failed me. I was hoping it had e on here. It does have logarithm. It does not have e. Or maybe I just don't even see it. Anyway, well, we know it is 2.7 to the, oh, I can't even do an exponent on here. Oh, here we go. 2.7 to the 7 divided by 2 power is about, this is very rough calculation. When I actually did it, I used my graphing tool. So x is about 33.11. I know that's not what I showed on my screen. That's because I used the wrong value of e. All right. And then again, any of these, we didn't actually do this with the logarithmic equation. That's why I wanted to do 90. If you look at our original equation and we go to our graphing utility and we graph our logarithmic equation along with our solution, we can find where the two intersect. So what I mean by that, we have 3 plus 2 times, and we want to do the natural log of x, and we want to know where that equals 10. To change my viewing window again, right? From -1 to 11. That's better. And then I forgot, Desmos always makes you, if you want to graph this, you need to say y equals 10 to define it, okay? All right, so it looks like my viewing window is okay on my y-axis, but I need to go out a little on my x-axis. And where do the two intersect? And that is where, when x equals 33.115. All right, guys, so that is fun with logarithms. That's the rest of 3.4. You guys should be able to tackle that, and I will do another video with 3.5, and we will talk when I get back. Thanks, guys. Thanks for watching. Bye.